Unmuted. Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and I'm joined today again by Francesca.
Hiya.
Francesca's one of our default students. He's going to show some maths today. Francesca's been on the stream before, back in season 1, I think episode 8, talking about epidemic maths. Link on screen above my face. If you're watching the replay, there'll be a link on screen somewhere. If you're watching live, then please don't go and watch the other one. Please watch the live one. Great to see you here. We've got people who are here live right now watching along at 5 p.m. on a Thursday. Just giving people a little while to join us in this live stream YouTube thing. I'm going to do some shout outs because I've got them on screen at the moment. Shout out hi to Molly, hi to Alice, hi to Mew with the username Mew, who asks me how I'm doing. I'm doing well, thank you. Lovely hot weather, which is always nice. Hi to someone called the Approach Guy, who's hyped. Hi to B again, Raphael, and George. And someone says finally, and I don't know whether they mean finally they're here for the live stream or finally something else. But hey, hi to Gamma as well. Hi to someone watching from Sri Lanka. Hello and live. Right. Fantastic. I should say, I say at the start of every live stream, if it's your first time watching, then hi, great to have you with us. This is a sort of maths club where we talk about maths and do bits and pieces of mathematics. It's supposed to be a sort of chill after school thing. There's no test, there's no grades. People are saying they missed last week, which is of course fine. The live streams you don't need to watch everyone in order. I've noticed the view count on like the first one before I'd really worked out what the format was. The view count on the first one is loads higher than the view count on like the second one. So everyone tunes in for the first one. Anyway, people are watching this one now, so that's nice. If you want to join the live chat, if you're watching live, we're over at slido.com/OOMC. You can use your own name, you can use an anonymous name, you can just be anonymous, you can join in, ask us questions about what we're doing, we're reading it live. Also, if you want to talk to us about, I guess, anything else. People are now taking a monopoly on registering Greek letters as usernames. Something called Lambda has arrived. So that's nice too. Okay, what else do I say at the start of the stream? I was going to script it at one point. We've also got further reading, which is posted on the Maths Club website. The Maths Club website is on screen somewhere down there in the bottom left, maths.ox.ac.uk/club. That's got further reading associated with each live stream posted sometime on the Friday after the live stream on Thursday. So if you check back at the weekend, there'll be more to read related to that. B's got a graphing calculator, so that's exciting. Oh, and the approach guy is first time, so possibly finally for first time actually watching live. So hi to people joining us watching live. Very exciting. Right, I've done all of my ramble at the start. It's getting longer. There's more rambling every one I do. Let's switch over to hi to Toast and Zach again. Sorry, hi. I'm still doing shout outs. Francesca, let's switch to your slides. I've seen your title, which I've put in the YouTube title as well, is Chaotic Viruses. So you're going to tell us something about virus research, right? And this is related to your work, right?
Yes, this is related to some work that I've actually done as part of my DPhil. So, yeah, I'm hoping you'll find it interesting.
Fantastic. Okay. I think someone would have said by now if we'd forgotten to unmute or if we'd broken something. So I think. Right. Somebody's asked me for Pythagoras' theorem in chat, so I'm going to go and type a response to Pythag, or maybe somebody else will. But let's make the most of the time. I'm going to hand over to Francesca to tell us about chaotic viruses. Thank you very much, Francesca.
Okay, no problem. Well, hi everyone. It is lovely to be back speaking at this online maths club. Some of you might remember me from a talk I gave last term on mathematical epidemiology and estimating outbreak probabilities. Today, I'm going to be talking to you about something a little bit different, still epidemiology focused because that is what I do. But this time we're going to be looking at viral evolution and building a mathematical model to help us understand how different strains of viruses can appear in populations over time, which also has some pretty cool applications for creating new vaccines. So I hope you're going to find it really interesting. Please do pop any questions in the chat as we go along. I can't actually see the chat, so James, if anything comes up, then please interrupt me and shout out questions as we go along. That would be great. So first of all, a little bit about me. So as I said, I'm Francesca, that is me on the left there, in case you couldn't recognize me. I'm a second year DPhil student at Oxford. I actually did my undergrad here as well. I studied the 4-year MMath course at Merton College, which you can see in the picture at the bottom here, very beautiful college. And I liked it so much that I decided to stay for my doctorate. So now I work in the maths department, in the mathematical biology research group, and my area of expertise is mathematical epidemiology. So using maths to understand how infectious diseases spread through populations and how we can control them. So as you might expect, in the last year, I've been doing quite a lot of stuff on COVID, but I also do a lot of work on plant diseases and also some other human diseases such as Ebola and flu, which is what I'm going to be talking to you about today, mainly. So after the whole of the last year and everything that has gone on with COVID, you really don't need me to tell you that developing effective vaccines against infectious diseases remains a really important area of research. There are lots of diseases that we do have vaccines for, including measles, diphtheria, hepatitis, polio, cholera, and of course smallpox, which is where vaccination really started, amongst others. However, there are also a whole bunch of really deadly diseases that we still don't have vaccines for. So things like malaria, HIV virus or AIDS, Zika virus, chikungunya, and then of course any new diseases that emerge like COVID-19 also then present a massive challenge for developing new vaccines, as you all know, based on what's gone on in the last year. However, the one I'm mainly going to focus on today is flu or influenza. And you might be wondering why I've put it in this yellow box in the middle. And the reason for that is, although we can and we do vaccinate against flu, we don't actually have a vaccine that will continue to protect you against all the different strains that keep appearing. So you'll probably know from personal experience that with the flu jab, you have to keep getting a new jab every single year, rather than just having it once and then being immune forever. So why is that? What is going on with flu that makes it different from these viruses or diseases in the box on the left? Well, if we take the measles virus, for example, so this is an illustration of a measles virus on the left, and I think they're not quite as cuddly looking in real life. This is something that's actually really ideal for vaccinating against. And the reason for that is that the immunogenic regions of the measles virus, so those are these bits that are called antigens that are sticking out of the surface of the virus. They're the bits that trigger the immune response. In the measles virus, these are actually really well conserved over time. So what that means is if you get infected once, like a natural infection once, or if you get vaccinated once, then that gives you a lifelong immunity to this virus because your immune system will just continue to recognize it every time it encounters it. And this is why actually the same measles vaccine that was developed in the 1960s is actually still able to provide protection against measles now, despite the fact it's half a century later, and why we've actually been able to more or less eliminate measles in many parts of the world because our vaccines against it are really successful. However, the same cannot be said for flu. So with flu, the influenza A viruses specifically, the antigens, the surface antigens, so these are these proteins, again, that are sticking out of the surface of the virus, they're really not conserved over time. Instead, they're actually highly variable. And that means that kind of year on year, we see different strains emerging that are able to evade the immunity that people have previously acquired from other strains. So just as a quick aside, this has nothing to do with maths, but it's just quite cool biology. The sort of two important antigens that you get on flu are called hemagglutinin and neuraminidase, one of which starts with an H, one of which starts with an N. And each of those two things have a lot of different sort of varieties. And that is what, like, where we actually get the naming system for flu viruses that you will have heard of. So things like H5N1, H3N2, it's referring to the types of the antigens that you get on these viruses. So that maybe gives you like a bit of a clue as to how variable they are, because there are so many different types. Now, the classical theory of what is actually kind of going on is that the virus is continually acquiring kind of small mutations, and they kind of accumulate, and it gradually evolves to escape the immunity that's kind of present in the host population. That's the classical theory, but that doesn't actually really match up with what we observe in reality, because if it's actually true that new strains appear as a result of the gradual accumulation of mutations, what we would expect is at any one time, we'd actually see a really diverse range of different types of the virus, different antigenic types that are all able to evade the existing immunity. And that's not actually what we observe with flu. What we observe in reality is the kind of sequential dominance of individual strains. So what I mean by that is we have one specific identifiable strain comes along, dominates over all other strains for a while, and is then replaced by another distinct strain. And this happens in a very unpredictable way. So the question is, can we use maths to come up with a theory that is able to explain this behavior and give us some insight into the way the flu virus actually mutates, which of course in turn would help us figure out how to develop better vaccines. And specifically, the kind of holy grail is to develop a vaccine that could protect against all the different types of flu, rather than just one type of seasonal flu and having to keep vaccinating year on year. So that's the question. You may have already guessed that the answer is yes, we can build a model to do this. Otherwise, I wouldn't be telling you about it. So you'll be glad to know that kind of the worst of the biology is over, and now some actual maths is going to appear happily. So the model I'm going to show you is called the Multi-Locus Model. So the way this model works is, take our virus, we assume that for a given antigen, there are K different bits of it that the immune system could respond to, which we will call loci. And each of those loci could display one out of a whole range of different alleles or different variants that are a little bit different in the eyes of the immune system. And any particular combination of these different things then defines a strain. So the total number of strains is a total number of different combinations. So say, for example, we have 3 loci, 3 regions on our antigen that the immune system can see, and then each of them could display 4 different things. Then in total, there would be 3 times 4 equals 12 different possible combinations. So here, I'm going to choose a very simple case to demonstrate the ideas, just because it gets quite messy quite quickly. So the more different regions you have, the worse it gets. So we're going to go with kind of the simplest case that can actually do something interesting. What we're going to do is suppose that our antigens, so this is represented by this Y-shaped thing on the left, has 2 loci, locus 1 and locus 2. And we're going to assume that each of them can choose between 2 different variants. So we're going to say locus 1 can choose between showing variant A or variant B, and locus 2 can choose between showing variant X and variant Y. And that means that in total, of course, we have 4 different possible strains, which we will call, unsurprisingly, AX, BX, AY, and BY. So they're the 4 different possible combinations of variants that we could have. And what we do is we suppose that everyone in our population is going to start off susceptible to every single strain. And then if you get infected with a particular strain, so AX, for example, you're infectious for some period of time, and then you recover and you become immune to that strain. And what we also say, and this is really important, so remember this, is that if you've been infected with a strain AX, you not only gain immunity to that strain AX, but you also gain some partial immunity or cross-protective immunity to strains AY and BX. And that comes about as a result of your immune system basically noticing something familiar about them. So it will see AY and think, okay, I haven't seen this before, but I kind of recognize that A. So I'm going to tentatively react to this thing. What we're going to do with this is build a differential equation model to understand how the amount of each of these different strains that is present in the population evolves over time. And we're going to see whether we can actually get the behavior that we observe with the flu. So that is, as I mentioned before, an unpredictable sequence of strains which take over one after another. We want to see if a model of this form can actually give us the behavior that we know is what we're looking for. So to do that, we're going to need some notation. Right, so we're going to let YAX be the proportion of the population that is currently infectious with strain AX. We're going to let ZAX be the proportion of the population that are completely immune to strain AX. So these are people who have previously been infected with AX. That's how you get complete immunity to that strain. And we're going to let WAX be the proportion of the population that have some kind of immunity to strain AX. So that might be a full immunity, or it might be a partial immunity. So these are people who have previously been infected with any of the three strains, AX, AY, or BX. They have some, possibly full, but definitely some immunity to that strain. So I've got these Venn diagrams here, which I'm hoping will help to clarify things a little bit. In each of them, each circle represents people who've been infected with one of the four strains. And then they're color coded to show you what things like ZAX and WAX and so on look like. So these are going to be kept on the screen for the next few slides, just because I hope that they're helpful in understanding what's going on. So for example, in this pink one on the left here, we have ZAX, the proportion of the population completely immune to strain AX is here in dark pink. And then the rest of the population, which is 1 minus ZAX, they don't have any immunity. They're the light pink region. Similarly, in this Venn diagram in the middle, WAX are the people who have some immunity to strain AX. So they're kind of the overlap of the circles representing AX, BX, and AY, but they're not this little bit. This light orange bit are the people who don't have any immunity to strain AX at all. This green one, we'll see why that's important in a little while.
Just to check, I think some of the letters are probably very small. I don't know how well it's going through my live stream setup. In each of your Venn diagram pictures, there are 4 circles. The top left one, I'm going to read them out really quickly. The top left one is all about the strain AX. The top right one is about the strain AY. The bottom left one is about the strain BX, which differs. A and B are different, but X is the same. And the bottom right one is all about the strain BY. And on the left, on the left is the people completely immune in pink. The orange one is talking about which ones have some immunity to particular strains. And then the green one, which is really complicated, it's quite a fun Venn diagram, isn't it? It's like one minus the other one, right?
Yeah, exactly. So those are actually people who have partial but not full immunity. So it's people who have had AY or BX, but not AX. And yeah, we'll see why that's important in a few slides' time. So these diagrams will stay up there. Apologies if the writing is a little bit small.
While I'm interrupting, there's a question in chat as well, sorry. So in your previous epidemic model talk, I think you talked about people getting the virus and then recovering or being removed from the population. Do they count in some of these proportions or not? The people who have died of one of the virus variants?
No, they don't count in these proportions. So these are all people who are actually present in the population that satisfy these properties. And what we'll see in a minute when we actually write down the differential equations is we're going to include terms that account for the removal of these people as a result of recovery or death later on. So these are proportions of people who are currently alive and, well, I guess not well, just alive in the population.
Alive and suffering from 4 different strains of some virus.
Yeah,
Okay.
exactly.
Good
Yeah, so
question.
we'll see that in a minute. But yeah, that is a good question. Cool. Any more
Okay.
questions while we pause? Or should I carry on?
I think we're good. we've got some parameters as well.
We have. Don't worry, you're not expected like to remember all of these things. There will be a little box on the next page that will have a reminder. And yeah, I'm not testing you on exactly which parameters which, so don't worry about it. It's just kind of for information. So yeah, this blue box that is in the bottom right here, these are some epidemiological parameters that we have to put in, basically because we need to make sure that our model is actually tailored to whatever disease it is that we're interested in. So we have things like the transmission coefficient, which is to do with the probability that a contact between an infectious person and somebody else actually leads to a transmission. And then we have things like 1/mu, which is the life expectancy, and 1/sigma, which is the infectious period. And those, again, are things that, well, mu doesn't really depend on the disease in particular. That's just a sort of general life expectancy. But the 1/sigma, which is the infectious period, of course, is something that depends on the disease, because for some diseases, you're infectious for much longer than others. So those are basically put in to account for some of the actual biology that's going on. The parameter that I do particularly want people to pay attention to, though, is this one, which is in red. This is gamma, and this is representing the strength of the cross-protective response. So what that parameter is basically telling us is how much will your immune system react to something that's a bit familiar, but not completely familiar. So how much will it react to strain AY or BX, given that it's seen strain AX before? And this is, as I said, a very important parameter for this model. So I will be continually reminding you what that parameter means, and we will look at that one in a little bit more detail later on. So now we have our notation, which I hope everyone is broadly okay with. Now we have that, we are ready to construct our equations. So, like I said, we've got a reminder of the notation over here on the right, and the Venn diagrams are still down here as well, just for you to refer to in case you've forgotten what they are, which you probably have, because I mean, there's a lot of notation here, so it's totally fine. So what we're interested in is how things are changing over time, right? We want to look at how these proportions are evolving sort of year on year. So that kind of naturally leads us to use differential equations where we're writing down the time derivative of each of our variables. So first of all, we're going to think about ZAX. So that is the proportion of people in the population who are totally immune to strain AX, or equivalently, the proportion of people in the population who have previously been infected by strain AX. So the question is, how does that proportion change over time? What is d by dt of ZAX? Well, people can become immune to strain AX if someone who isn't already immune, so that proportion is 1 minus ZAX, that's everyone who's not already immune, comes into contact with someone who is infectious with that strain, and that's the YAX term. That's how you can actually get infected with that strain and gain immunity. And what we do is we scale that with our transmission coefficient beta, which, as I said, is basically the probability that that contact actually leads to a transmission. And then, as I mentioned before, we can also lose people who are immune when they die, and that happens at rate mu. So our life expectancy, as I said before, is 1/mu, and that means that sort of the rate at which you die is given by mu. So we remove them at rate mu, hence this minus sign. And what we end up with is this equation for d by dt of ZAX. How is ZAX changing over time? So now we've got that, we're basically going to do similar things for the variables WAX and what's the other one? YAX. So for WAX, That is the proportion of people that have some immunity to strain AX. It could be full immunity, it could be partial immunity. So this is going to be a similar kind of equation to the previous one, but we need to take into account the partial immunity as well as the full immunity. So how can you gain partial immunity to strain AX? Well, you have to be not already partially immune to strain AX. So that's this 1 minus WAX term, everyone who's not already partially immune. And then you have to come into contact with somebody who is infectious. But remember, because we're thinking about partial immunity, this infectious person, this YPQ term, they could be infectious with AX, they could be infectious with AY, they could be infectious with BX. Any one of those would lead you to have some partial immunity to strain AX. So what we have to do is sum over those different possibilities. So this notation here might look a bit weird. This PQ squiggle AX is basically just saying, let's sum over anything that has something in common with AX. So PQ here could be AX, it could be AY, or it could be BX. That's all that means. We're taking the sum of these terms for each of those different values of P and Q. And then just as before, we can lose people who have partial immunity when they die, which again occurs with rate mu. So we take away this term minus mu WAX. So this is our equation, which is describing how the people with partial immunity evolve over time. And now finally, we have to write down an equation for d by dt of YAX, because of course, if we go back to the previous slide, we've got these Y terms in here. We need to know what they're doing as well. Otherwise, we can't possibly figure out what's going on with the W's and the Z's. So we need to write down an equation for YAX as well. And remember, they're the proportion of people who are currently infectious with strain AX. And that's actually what we're particularly interested in. So this one's maybe a little bit more complicated. So how does someone become infectious with strain AX? Well, we have to have a person who is already infectious with strain AX. So we have to have a YAX person already there. And then there are a couple of possibilities. So firstly, they could get in contact with someone who has no partial immunity to AX. So that's given by this proportion 1 minus WAX. And then they could infect them. That's fine, that can happen. Alternatively, they could contact someone who has partial but not total immunity to AX. So remember, if we have total immunity, you can't get infected again. So that's why we're not considering those people here. We're only considering people that have that don't have full immunity. So this WAX minus ZAX term, this is where this green Venn diagram comes into play. So these are all the people who have seen or been exposed to AY or BX, but not AX. So they have some immunity to AX, but not full immunity to AX. And since they have a partial immunity, they are less likely to be infected. So what we do is we scale that term there with a factor of 1 minus gamma, where gamma, if you remember, is this very important parameter, which is representing how strong their partial immunity is. So the reason why it's 1 minus gamma is because a very strong partial immunity, that corresponds to a very large gamma, which then corresponds to a very small 1 minus gamma, and that is therefore a small chance of getting infected. So that's why it's a 1 minus gamma term here. And then as well, we can lose people who are actually infectious with this strain when they actually recover at the end of their infectious period. So we're removing those people from the population. And this happens with rate sigma, where 1 over sigma is the duration of the infectious period. So I hope you kind of followed all of that. I realize it's a little bit complicated. Just to sort of sum it up, if we do that for each of the other 3 strains as well and put it all together, we end up with this slightly terrifying looking system of differential equations. Now, don't worry if this does look pretty terrifying, because it is quite a complicated system and you definitely don't need to remember all the nitty-gritty details of this for the rest of this talk. These are pretty ugly equations. We're definitely not going to try and do anything analytic with them. In fact, we're just going to get a computer to solve them for us. To be honest, this is almost always the case in mathematical biology, simply because biological processes are just so complicated that any equations that we use to describe them are necessarily also pretty messy. So unfortunately, it just sort of comes with the territory. So don't worry about it particularly. The important point that I want you to take away from this is that with just a little bit of insight into the biological mechanisms that are going on, we can write these equations down, and that gives us a way to understand how these quantities are changing over time. That's the main point. That's the main point of this. So just to break these equations down for you a little bit, the W's, the Y's, and the Z's are our variables, of course. We don't know what's going on with them. That's what we're trying to figure out. These parameters in blue, the beta, the mu, and the sigma, these are parameters that in theory we know because we choose them to fit the specific disease that we're interested in. And I know quite a lot of people in my previous talk were interested in how we actually estimate those kinds of parameters. Like, how do you choose like the transmission coefficient for a given disease? How do you choose the mu? You know, how on earth do you know what these things should be? And the answer is, you basically have to have some kind of real world data for these things. You have to have measured cases of this disease enough times to know how long it takes people to recover from it, and that kind of thing. You have to basically have that information. For something like flu, that's not too difficult because it's a disease that we have a lot of information on, because it's been, you know, flu outbreaks, flu epidemics, pandemics have been happening for a very long time. And, you know, we have a lot of information on them. So actually choosing these kinds of parameters for flu is not so hard. When it came to something like COVID-19, it was a lot more difficult because there was a significant lack of data right at the start of the pandemic. So choosing parameters to fit a specific disease when you don't really have any information about it is very difficult. So yeah, essentially you're choosing them to make your model fit in with real life predictions. That's where they're coming from. So yeah, in theory, we know what those things are. So for our purposes here, we're just going to set them equal to some given numbers and not particularly worry about them. They're not the important things. The parameter that I really want you to remember, as I said before, is this red one here. The gamma, that's the strength of the cross-protective response. And that is something we don't really know anything about, because this is kind of a theoretical parameter that we've just introduced to sort of make our model sort of, investigate something that's going on with our model. So that's the one that we're going to be varying and looking at how the behavior of the system changes as we vary that parameter gamma.
Questions from chat, sorry to jump in.
Yeah.
Okay, can we look at your equations again, sorry. So firstly, I'm just going to look down the camera and say all the variables are real, team. Loads of people in chat want to use complex numbers. I suppose I and J are real. In fact, I is just going to be A or B, and J is supposed to be just X or Y. So this is just some notation. Some notation to explain. There are different strains out there. So these subscript IJs are the names for the different strains. They go AX, AY, BX, BY.
We just use that notation so we don't have to write the same equations out 4 times for every different combination of I and J, that's all. Yeah.
Right, so people, yes, there's some really compact, it could be much worse if you wrote this equation out for AX, for AY, for BX, for BY, 4 times as many equations.
And this is actually 12 equations rather than 3, so it's a lot nastier than it looks, but yeah.
And then people are breaking down other bits of it as well so as well as wanting to make things complex by putting in complex numbers.
It's complex enough.
Yeah. So people in chat, the approach guy and an anonymous question right at the top of chat at the moment, want to think about whether this gamma parameter, which is a little bit mysterious, this extent to which once you've had one of the strains, how immune are you to the other strains? Thinking about maybe that could vary from person to person, or maybe it could vary from strain to strain. I don't know.
Yes, that is a very insightful point, and in fact is absolutely true, and it's not something that I was really going to cover in this particular talk, just because it's kind of complicated enough as it is right now. But it is definitely the case that gamma might not be the same from strain to strain. It might not be the same from individual to individual. And actually some work that I have done as part of this project is to look at what happens if you have, let's say, 2 groups within the population who, for whatever reason, maybe it's age, maybe it's something else, they have a slightly different immune response. And how does that actually affect the dynamics of the system? And it's actually like a very deep and interesting question that doesn't have like a very easy and straightforward answer that I can just say right now. So I think I'll just leave it at that and say, you're absolutely right. That is a very interesting question. And you can get some very cool results if you actually kind of relax this condition that it's the same for everything, definitely.
And someone in the chat's just suggested that maybe you could think of doing a sort of weighted average or some sort of replacing the complicated picture of what might actually be going on in the real world with this kind of simplified, let's see what happens if we just have the same gamma for everybody and the same gamma for all the strains. Which I think is quite a sort of mathematical modelling thing to do.
Yeah, definitely. I mean, in mathematical biology in particular, when you're trying to model a biological system, in reality, these things are so incredibly complicated that you have to make some kind of simplifications. You have to decide what it is that you really need to include in the model and what it is that you can actually kind of approximate or simplify or say, okay, it's not that relevant. Just because if you try and account for everything all the time, your maths would be so complicated that you'd never get anywhere with it. So yeah, it is always just a question of basically trying to write down the simplest model that actually does what you want it to do. It's a bit of an art form, really. It is an issue kind of overall.
There's always that challenge of choosing between maths that we can do versus stuff we want to understand, and trying to bring the stuff we want to understand down one way and the maths we can do up the other way.
Exactly. And I mentioned this again in the previous talk when people were asking about, how could you extend this model and make it more complicated? The answer is, you can always make your model more complicated, but there's a bit of a trade-off with if you make it more complicated, then you're going to end up having to choose more and more parameters for it. And it kind of is a bit of a balance between making it realistic in either way, because if you make it so complicated that the data is not available to parameterize it, it's not actually helpful or more realistic in that case. So sometimes keeping it simple is actually better. So you have to sort of judge it based on the situation, really.
There's something called overfitting as well, which I'm going to mention now because I feel it's like the right moment. That if you have a very complicated thing in the real world that you want to explain, it's really complicated. Here, different flu strains seem to do different things in different years, rather than just one flu strain winning all the time. That's a really complicated observation. If we can explain that with a simple model, then it shows that the model's got some important insight in it. If you build a complicated model and it does the thing, then in some sense, there's still loads of things in the model that could be doing it. But if you can get it down to a simple model that does it, then maybe you found out a good reason of why that thing's happening, which is a sort of science question that we ask sometimes.
And as we'll see, actually, this parameter gamma, which is really important, we get some really cool behavior just by varying that. And the fact that our system is so simple means we can actually attribute this behavior to the variation in gamma. Whereas if you have loads and loads of things that you're trying to vary all at the same time, it's actually quite hard to figure out what it is, like what is the causality, what is the thing that's actually making this happen. So.
Sure. Well, we've had scary equations on the screen for quite a while now.
Maybe everyone's got used to them and they're less scary now. I don't know.
There's the sum over PQ tilde IJ. That's a little bit we're talking about a little bit in chat as well. Okay, you've got some terrifying equations. What are we going to do with them?
Yes, good question. So, like I said, it's not a very nice system to try and solve analytically at all. Like, I wouldn't want to go there. So what we're going to do is get a computer to do it for us, which again is sort of very standard in mathematical biology just because of the complexity of the systems. So computers can solve these things a lot faster and a lot better than we can. So we're going to do it numerically. So just to give you a little taste of that, what we'll need to tell the computer is a list of the things it needs to know. It needs to know the number of the different loci and the different variants present at each locus. We need to tell it, obviously, the system of differential equations that we just wrote down. We need to give it our choice of our epidemiological parameters that we know, the beta, the mu, the sigma. We can feed in our choice of gamma and vary that and see what happens as we vary it. Then we also need to give it some initial conditions because it needs to know where to start from when it solves something numerically. So I'm sure you'll have come across, solving differential equations. And if you don't have the initial conditions, you kind of end up with integration constants and that kind of thing all over the place. And similarly, when you're solving it on a computer, the computer needs to know where to start from. Otherwise, it has no idea what's going on. And then we just need to give it some other sort of computational information. So things like how long do we need to run the simulation for? What exactly do we want to plot? What is the information we want to extract? All of that sort of thing. So you take all of these things and then you code them up in whatever programming language you like. So for me, that's MATLAB. It's my favorite one. It's great. And what MATLAB will do is do all the heavy lifting for us, do all the hard work, and then if you code it right, at least, and don't make any errors in your code, what it will spit out is time series for each of our variables. So that means basically all the information on how the Z, the W, and the Y variables change over the whole time period that we've considered. And what we're going to look at particularly is the Y variables, which is the proportion of people infectious with any given strain and how that changes over time. So what we're going to do is plot some graphs that look something like this. So on the x-axis, we're going to have time. On the y-axis, we're going to have the proportion of people that are infectious. And then we're going to plot that proportion and how it changes over time for each of our 4 strains, AX, BX, AY, and BY. And they're each going to have a different color and all be plotted on the same graph. So you can compare exactly what's going on between the different strains and how they're evolving over time. So that's what the graphs are going to look like, something like that. But obviously they're going to have like an actual graph and not just like random letters and a question mark on them. So first of all, what we're going to do is look at what happens when we have a low cross-protective response. So if we take this parameter, gamma, and set it equal to 0, that means that there is no partial immunity whatsoever. And that means you can only gain immunity to strain AX by being infected with strain AX. And that doesn't give you immunity to any other strain. So what that means is these strains are basically totally independent of each other. There's no competition between them, no natural selection going on. They can all just do their own thing without worrying about what any of the other strains are doing. That's if gamma is 0. I'm going to tell you now, the same is true if gamma is small enough. And what exactly small enough means, I'll come back to in a little while, because I realize that that is frustratingly vague. So I will come back to that, I promise. So in this case, I'm going to choose a gamma that is quite small. I'm going to choose gamma as 0.3. And if we run our simulations and solve those differential equations numerically with that value of gamma, then this is what we get. So remember, here we've got time on the x-axis. The y-axis is the proportion of people infectious with each strain. And then we've got each of the 4 strains in the different colors, blue, red, yellow, and purple. And this is how those strains are changing over time. And what we can see is it's all a little bit crazy in the beginning. And this is just because we're chucking these 4 strains into a population that's totally susceptible. And it all just goes a little bit crazy while they kind of do their own thing. But then eventually, sort of in the long term, what we see is that all 4 of these strains are basically equilibrating to kind of coexist together at a constant level. And this is because they're not competing with each other. So they can all just coexist quite happily, kind of independently of what any of the others are doing. Now, this scenario is what we call no strain structure, because there is no structuring going on between the strains. So it's quite a logical name. And although the graph does look quite pretty, it's not really what we're looking for, because this definitely isn't the kind of behavior that we see with flu. Remember, what we're looking to see is if our model can reproduce this kind of very unpredictable, continual, almost random dominance of a single strain over any other at any particular time. And although it might kind of look like that's what's happening at the beginning here, it's not really. That's just sort of an equilibration phase. And by the time we get over here, it's not very interesting. So although it's cool, it's not what we're looking for. So what happens if instead we make the cross-protective response really, really high? So if, for example, we set gamma actually equal to 1, that means that there is total cross-protection. And what that means is that being infected by strain AX gives you total immunity, not only to strain AX, but also to strain AY and strain BX, because they have something in common. And your immune system says, I know A, or I know X, I know these things as well. However, it doesn't give you any immunity to strain BY, because they don't have anything in common. They don't share any alleles. So it can't recognize a B, it can't recognize a Y. So in this case, what we might kind of logically expect to happen is that the strains will actually kind of naturally group themselves into what we call discordant sets. So in this case, this is basically pairs of strains that don't have anything in common with each other. So one set here would be AX and BY, and the other set would be AY and BX. And within those pairs, each of those pairs can get along with each other just fine because they're not competing in any way. However, the two pairs of strains are competing kind of with each other, with the other pair. And so if we actually run our simulations again, and in this case, setting gamma equals something quite high, so I've chosen 0.9 here, then we actually get exactly what we would expect. So here we've got the blue and the purple lines. These are representing strains AX and BY. And they're going along quite happily together. They're doing great. And the other pair, which is the red and yellow lines, so you can't really see the red line. So you'll have to take my word for it. It's basically hidden beneath the yellow line at the bottom here. Strains BX and AY are just completely flatlining. And basically what's happened is they've been forced into extinction by the dominant pair. And the reason why blue and purple kind of won over red and yellow is simply due to the choice of initial conditions. So they were chosen randomly, and in this particular case, it just happened that the blue and the red ones, AX and BY, maybe just had a slightly higher prevalence at the beginning that just gave them a bit of a competitive edge and could force the others into extinction. So this...
Ooh, sorry.
Yeah, go ahead.
In that case, are people here completely immune to strains 2 and 3, the BX and AY, or is it just that gamma is so large that they've got lots of partial immunity? I'm sort of struggling with the wording.
So if gamma is 1, so that's as high as gamma can be, the biggest it can be is 1. If gamma is 1, then that means if you are infected with strain AX, you're completely immune to AX and to AY and to BX. However, in this particular figure, I've chosen gamma is equal to 0.9, so a little bit less than 1. So in this case, it's not quite the case that if you have been infected with strain AX, you're guaranteed to be completely immune to those other two. But your immune response is big enough that in combination of AX and BY, it's sufficient to still force these other two strains into extinction. Even though it's not complete, it's enough. So,
and you as a person don't actually need to contract both strains. Once you've got AX, you're pretty much almost immune to both BX and AY because they share a
exactly.
letter. I guess you're not immune to BY, and that's why the other one. Okay,
yeah, exactly.
That's why they're taking it in terms.
That's why these two, the blue and purple ones, are kind of coexisting happily, because being infected by one has absolutely no bearing on whether you can get infected by the other one. So they're not competing with each other. They're quite happily coexisting. But being infected with either of those means you can't get infected with the red one or the yellow one. So because the blue and purple ones started out a little bit dominant, they were then able to sort of squash the other ones to an extent where they basically can't come back because everyone's already got some kind of immunity to one or the other.
And they're sort of taking it in turns, aren't they, to looking at the peaks?
Yeah. If you look at them, they're kind of oscillating sort of out of phase with each other, yeah.
Okay, but I guess that's not what we see with actual flu, where it's not just the case there are two.
No. So again, this case is very interesting for reasons I will actually come back to in a little while, but it's still not what we observe with actual flu. So with actual flu, what we see is a much more chaotic kind of behavior. So we see kind of at any particular time, one specific strain is going to massively dominate over all of the other strains that might be in the population. And then suddenly that one will basically disappear and a new strain will just take over and massively dominate. And we don't get any kind of equilibration. We just get like a very random strains just spiking up kind of throughout time continually, and it's very unpredictable. So yeah, this is still not what we actually observe with flu. This is what is called discrete strain structure, just because our strains are segregated into these sort of discrete sets that don't overlap with each other. So we've looked at low cross protection, we've looked at high cross protection. I guess the obvious question is, what happens when our cross protection is medium size, when gamma is somewhere in the middle? So what if gamma is somewhere in between? Well, what does that actually mean? That means that being infected by strain AX still gives you total immunity to strain AX. You can't get that one again. And then it gives you some partial immunity to AY and BX, but not a really strong partial immunity to them. So who knows what's going to happen in this case? Well, the answer is, if we run our simulations, this is what we get. So this is what I was talking about with the kind of chaotic behavior and particular strains suddenly massively dominating over all the rest of them. We're seeing sort of individual strains sequentially taking over in a very unpredictable way. So, I mean, if you look, for example, at time 150 and see what's going on there, knowing what's happening there doesn't in any way help you figure out what's going to be happening at time 200. This is what I mean by unpredictable. You can't really tell easily what is going to happen next. It's very chaotic. And this is because of what we call immunological interference. So this is what happens when there's enough of a competition between the strains that they can't all coexist, but there's not enough of a competition for some of them to actually force the others into extinction. And so we get this behavior where they're basically just all continuing to fight it out amongst themselves. So this is known as chaotic strain structure. And this is very cool because this, in fact, is exactly what we do observe with flu. So with this quite simple example, remember we only have two loci and 2 variants at each one, so only 4 strains in total. With this quite simple example, we've managed to generate this really complex behavior that is actually characteristic of real life flu epidemics. And that gives us some insight into the way that flu viruses actually mutate and how new strains actually arise in the viral population. Now, I did promise I would clarify exactly what is meant by gamma is small enough or gamma is large enough. So just quickly, here is a way of actually quantifying exactly what I mean by that. This is a measure which is called single strain dominance. And it basically describes the tendency of the system to be in a state in which a single strain is dominant at any given time. So it's actually given by this formula on the left here in this purple box. And what it's doing is looking at capital P different time points. And at each one, it's working out difference in the prevalence between the most common strain, which is Y max, and the second most common strain, which is Y sub. Now, in the first 2 cases that we looked at, so this one in the bottom left and the one in the bottom right, we always have at least 2 strains that are coexisting at the same level. And so Y max and Y sub are basically the same or very close to being the same all the time. So this measure epsilon comes out as being 0 or very, very close to 0. But when we have the chaotic behavior, the most dominant strain is always a much higher prevalence than the others. That's basically the definition of this type of behavior. And so what we get is Y max is a lot bigger than Y sub. And so this measure comes out as being very large, by which I mean close to 1, because it always has to be between 0 and 1. So in this graph in the middle here, we're basically varying the strength of the cross-protective response, varying the parameter gamma. And what we're plotting is this measure of single strain dominance. And you can clearly see this big kind of mountain in the middle that corresponds to the range of gamma for which we get chaotic behavior. So in this case, small enough meant less than, I guess this is 0.5 here, and big enough meant bigger than 0.85. So we can actually quantify that in case anyone was interested in me clarifying that slightly vague point. So just to finish off, I want to tell you how all this modeling could actually help us to design a vaccine. So for that purpose, for designing a vaccine, what you're actually interested in is finding antigens or loci that have the discrete strain structure, which is the one that is shown here. Now, the reason for this is when you're making a vaccine, what you want to do is you want to find regions that produce a really strong immune response. but you also want those regions to not be too variable. That's how you'll actually end up getting an effective and long-lasting vaccine. And what this graph is telling us, why it's so interesting, is that strong immune responses, so we have gamma is 0.9 here, that's a strong immune response, acting on some regions that aren't particularly variable. So in our case, remember, there's only 2 possible variants for each site. So low variability still manifests in the viral population as this kind of discrete strain structure, which basically means an imbalance in the frequency with which certain pairs of genes are appearing in the population. So for example, if you look at some samples from your viral genome, you go and take a whole bunch of samples from loads of different people and sequence them, and you find a pair of loci which only ever display AX or BY and never AY or BX, that's a pretty sure sign that those sites are actually under a strong immune selection, as is shown in the graph on the left here. And if that's the case, then they would be ideal targets for a new vaccine. And actually, there's a lot more cool maths which is involved in identifying those sites, because once you've done all of the lab work to actually sequence the viral genomes, you need some way of figuring out which sites are actually showing this imbalance. And to do that, we actually use some very cool methods from statistics and information theory to identify likely candidates. So I won't go into all that now because I'm kind of running out of time, but it is a really exciting direction for vaccine research at the moment. So I will stop talking now. Thank you very much for listening. I hope you found it interesting, and I'm very happy to answer any questions that have come up in the chat.
Thank you very much, Francesca. That was really interesting, and I really liked the different sorts of graphs and the way you just casually had the chaotic output in there, and people are asking really good questions about chaos. I think I'm going to answer some of them in the further reading, because I was going to put something about chaos in the further reading anyway. But let's read out one of these. Is it possible, somebody asks, to have a case where there's an equilibrium with strains, so 2 of the strains are kind of in equilibrium, but the other 2 strains haven't been completely knocked to 0? Can you have maybe 2 of them balancing and then the other 2 sub-dominant balancing but not 0-ish?
Yes, you definitely can. You definitely can have that. So it kind of all depends on what exactly is the strength of the cross-protective response. How much competition is there actually going on between those 2 groups of strains? So that definitely can happen. The other situation that can happen in, of course, is in the first case, we'll go back to it. Where are you? In this case, the only reason why these are all kind of equilibrating at the same level is because the parameters that I've chosen just mean that they're all kind of equally fit in terms of natural selection. So none of them has any particular advantage over the other. But in reality, of course, you could have the transmission coefficients, for example, for different strains are actually different, in which case some of them do have a slight advantage compared to the others. And if that happens, what you can actually observe is the strains all equilibrating, but at different prevalences in the population, depending on how infectious they are, for example. So there's all sorts of different behaviors that you can get depending on exactly what your parameters are, what you're interested in varying. Yeah, I mean, what I've shown you here only really scratches the surface of kind of the 3 main types of behavior, but there are a lot of other things. So yeah, it's a great question.
Yeah, lots of different complicated behaviour, including chaos. Chaos in the further reading. Check the maths website tomorrow, everyone, or over the weekend, depending on when I put it up. So cool. Toasters reminded me that I was going to ask a question ages ago. It's about the Venn diagrams. Can we look at the Venn diagrams again quickly, please?
Where are they?
We're trying to work out for the pink ones on the left.
Yeah.
Is it possible that someone is in none of the circles? I think they could be in none of the Z groups, right? If they're not immune to any of them.
So in the pink one, so these are representing people who are, immune or, have been infected by each of these different strains. Okay. So actually, I guess you're right. But anyone who's outside the circle has not been affected by any of them as well. So I guess strictly speaking should be included in the 1 minus ZAX, yeah.
Okay. Thank you, Toast. So I said I'd ask, and then there wasn't a good moment. But yeah, strictly there are people. Okay, there are people who don't do that. And somebody would like to know why. And I think this seems like a reassuring thing to end on. Somebody would like to know why all your graphs say 10 to the minus 3 at the top of the graph.
Let's see.
So these are your graphs of proportions and your y-axis.
These are graphs of proportions within a population. So times 10 to the minus 3 is like thousandths of a population, right? So, I mean, with flu, I mean, it is a very infectious thing, but you're not necessarily going to expect like the entire population to get infected with it every single year. To be fair, these graphs, I guess, are sort of somewhat arbitrary in the sense that I've kind of picked a population size, a given population size. I don't remember what that population size was. I made these graphs a while ago.
It's all proportions, isn't it? So then
it's all proportions.
Maybe it doesn't even matter, but
maybe it doesn't. Maybe it does. That's another question I won't go into. Yeah, they're all proportions, which is why they are actually very small. Which, as you said, is reassuring because we don't want the whole population to be infected at the same time. That would not be good.
Thank you very much. There's just time for Molly's fun fact of the week, which is 2 facts about Euler. Molly says these are not fact checked, by the way. Molly doesn't send them in before. Molly posts them and I read them out. So whether or not, with no independent research. Molly's fact of the week now is Euler's house burned down during the Great Fire of St. Petersburg, and he went blind when he was 50. I don't know if that's 1 event or 2 events. Anyway, thank you, Molly, for the fact of the week. Unrelated to today's maths content, but that's okay. That's going to be, I think we'll wrap up there. I'm going to hang out and chat a little bit. People are talking about chaos a little bit, and I can never resist a chance to talk about chaos. Thank you again, Francesca.
No problem. I hope people find it interesting.
Always great to have you on the live stream. We're going to wrap up here, I think, on the live stream. We'll see you again in 167 hours for another episode of the Oxford Online Maths Club. Have a nice evening. Take care. Bye.
Bye. Bye.